Hello and welcome to another creative coding video. It's actually been a while since the last one. I guess we've been a little bit busy with a few other projects, but I'm really pleased to be back again because I was inspired by a really great teacher of both Python and creative coding, Alexandre Villares. I'll put the link to his Twitter feed in the description. You should really explore his work. He does a lot of experiments, he tries new ideas, and he's a fantastic Python teacher as well. But this little sketch that he did really got me thinking, because it combines a few ideas. One is about the kind of trigonometric functions, the sine waves that we've looked at before, the functions that create kind of wavy shapes, and he combined it with the 3D way of building shapes to create something that looks like a ball or a sphere or a marble with some patterns on it. And I kind of looked at it and thought, wouldn't it be great to try and maybe build something that looks like a marble, those little glass things with patterns inside them made of, ink, So we won't create exactly something like this, but we will explore some of these similar themes as practice, really. So this video is not really introducing anything particularly new. What we're going to do is to take some of the ideas, the basic ideas that we learned previously, the things that we did introduce for the first time, and apply them in interesting ways. And that's always good to do, because almost all of creative coding is doing just that, taking basic ideas and combining them and applying them in interesting ways. So that was the inspiration, and as I said, I really encourage you to look at his work. It's really accessible, it's really friendly, and really kind of inspiring. So to start with, we are going to look at curves and building curves. Now, you've seen in the past how we have a kind of a coordinate system, x and y, and we can build shapes like circles and squares and rectangles, and we specify their location and then their kind of widths and heights or radiuses. Now, with curves that are kind of arbitrary in some sense, what we do is we have our canvas with a kind of coordinates on them, and then we pick points, we specify points where the curve goes through, like this, and we can choose to have that closed as well if we want to. So that's an easy way of creating curves. You'll see why we'll need them in a minute. We've actually done this before, so this is a bit of a refresher. And if you remember also that the P5 canvas actually starts its 0, 0 at the top left, 0, 0. Our default is 800 across and 600 down. So that might be a little confusing if you've been away and been looking at other graphic systems, where typically you start 0, 0 in the bottom left and x grows that way and y grows that way. But here we have 0, 0 in the top left. X goes across to the right as usual, but y goes down. It's not a major issue. It just can be surprising sometimes. So let's do that. Let's remind ourselves how to create curves. So we're logged into Open Processing as usual. If you're new, I would recommend going all the way back to the beginning of this YouTube channel, where we build up the very basics about how code works and how to code on the web like this, and just go through the very simple things like shapes and color and location. And if you go through that, you'll realize that we always pick a library. We enable it in like this. Where is it? It's called Simple.js. There it is, Simple.js, and we've just made sure it's enabled like that, and what that does, it gives us some nice easy functions to use, and it sets up this environment in a way that's beginner friendly. So we'll enable that, simple.js. I've also just made sure the text size is a little bigger so we can all see what we're doing. Great, and we set up simple as usual, and just to test everything works, I'm going to draw a circle at 400 across, 300 down, which is the center of the canvas, radius 200, just to make sure that everything works. Yep, there's a circle. I've been away from it for such a long time, I just wanted to check. Great. Now with a curve, we are specifying a few points that the curve goes through, and we have to enclose them in a shape. So we do begin shape, and then we do end shape, and then we can say close if we want the kind of the loop to be kind of the end to be joined back to the beginning. And we specify curve vertex, and let's just think of a number, say, I don't know, 400, 300 down. That's in the center. And now let's do another one that's 500 across, but the same down. And let's do another one that's at 400 but 200 up, and maybe one that's at 300, 200, just to see what that looks like. So these are the points that we want the curve to go through. Let's see what that looks like. There you go. Yep, those are the 4 points that the curve goes through, and we can add more. We can sort of put something in the middle there just to make it go back to the center there. Can you see how that works? So if we create a little loop, we can make it easier to create interesting curve shapes. You're probably seeing why we're talking about curves, because we want to create the inside of that marble with curves in some way. So that's the connection. Let's create a little loop that repeats, say, 5 times. Again, if you're not familiar with how to create loops, which are sections for repeating code, go back to the very early tutorials that introduce the idea of repetition and introduce a very simple way of doing it, as well as this more standard but slightly more verbose code. So I do recommend you go back if you're new to this. So just as a refresher, if you've been away for a while, this sets a counter, starts at 0, increases by 1 every time, and it repeats as long as I is less than 5. So 0, 1, 2, 3, 4. It won't be 5. That then it'll kind of jump out of this repeated section. So in this section, we're going to create curve vertex points, and we're going to make them random. So random number and another random number between. I'm going to keep them away from the edge of the canvas. So instead of going from 0 to 800, go from 100 to 700, and then 100 to, instead of 600, it's 500. Let's see what that does. Oh, cool. Let's run that again. Let's add more points. So instead of going 5, we go 10. So this curve should be, there you go, a little bit more cool. Notice the colouring scheme where it overlaps itself. It doesn't colour. Now you can change what it does, but for us we're not interested in that today. But if you're interested, you can certainly have a look. I mean, we could stop there. This is quite nice abstract art as it is. Maybe I should have done a video just on abstract art with curves. Don't know why this kind of has flavours of Juan Miro or Picasso. I don't know why. Great. Okay, so that's just to refresh ourselves on curves. Now we're going to draw curves inside a marble, and the curve is going to be almost like a surface. So let's think a little bit about what 3D looks like in a marble, what the kind of coordinates, how they work. Right, so let's remind ourselves of trigonometry. Now you'll remember, looking at just a circle now rather than a sphere to keep things simple, if this is an angle, let's call it phi, and this is the radius, let's call it r, we need to define and specify positions like the points that a curve goes through in terms of x and y and also z when we're thinking about 3D. When we're moving around a sphere, it's what we call polar coordinates. We define how far from the centre a point is. Let's do a different colour there, that point, and how far around. So we can either have polar coordinates, and they're quite convenient, 5 out and then 30 degrees around, but actually we need to convert that to x and y, and the way that works is with identities that you're probably familiar with by now. If you're not very mathematical, then you can just think of these as just by definition true. So r sine of theta, and this is x equals r times cos of theta. If you are more mathematically inclined, you can read all about the history of where these come from. But you can see r plays a role here because it must, because the bigger they are, the bigger the x and y's are going to be. And sine and cos are those trigonometric functions which relate the x and y to the how far around something is in a circle. So those are the identities, and if you've been following the tutorials, we've done this loads, you'll know these by heart. So if this wasn't let's move from a flat sphere, because we've done that lots of times before, into something that's 3D. Right, let's imagine we've got a sphere, and I'm just going to draw these things just to help us visualize the fact that it is a sphere. And what we can do is we can say, right, let's take a slice of across that sphere, which will be a circle, and we could say that for a point, let's say there's a point, I'll change colour, let's say there's a point here, we could say we define x, y and then z up that way. So this x and y could be just what we did before. We can say phi, so that y equals r sine theta and x equals r cos theta. That's just what we did before. So that will kind of give us part of the answer in terms of x and y if we're taking kind of horizontal slices. But what is r? It's the distance from this kind of polar axis out. Now you can see that near the top that radius is going to be small, and here along the equator is going to be the biggest, so that's not constant. So what is r? Well, r is, if we take that sphere again, looking at it more cleanly, this is the r, isn't it? Because if we do it at the top, it's small, and if we move down it gets bigger, and if we're here it's the biggest. So here R is the actual, let's call it kind of italic R, the actual radius of the sphere, but it's moderated a little bit by this angle. Let's call that alpha. So that R equals the big capital R, the italic R, times, is that sine of alpha? Yep, sine alpha, alpha, not theta. So this thing is that R. So there's two steps here. We're working out what the radius is, depending how far from the equator, how close to the poles we are. That gives us the effective radius of the sliced circle, and then we can work how far around the planet, as it were, we are. I hope that's clear. If not, say so in the comments and we'll revisit this point. So just to summarize there, we then have y equals, instead of that r, we got the big R of the actual radius of the marble. That's this thing here, dot sine alpha, that's this, and then sine theta. And then we've got something very similar, sine alpha cos theta. And again, if you're not very mathematical, that's okay. The best way to look at this is to say, well, it has to depend on the big R, the radius of the actual marble. It has to depend on alpha, which is indicating how far around we've gone from the North Pole. And it has to depend on theta, which is how far around we are the Earth. You know, are we at Europe, or are we around Asia, for example? Great. So those are, and again, some of you will know these mathematical identities already, but it's nice to see how they work and where they've come from. So that gives us the x and the y. What was the z? The z. It was how far up we are, which is the big R cos alpha. That's it. And that doesn't matter, it doesn't depend on theta, because it doesn't matter how far around we are. So we've got z equals big R cos alpha. Should have drawn a bigger rectangle there. So those are the three XYZ expressions. Let's get back to coding. Right, so we have to set up our canvas to be 3D now. So we have to recreate it. We create canvas. Now this is already done for us. A create canvas is done with a setup. In fact, Simple creates one that's 800 by 600, but we're going to overrule that now. We're going to say we create another one 800 by 600, and it's going to be of type WebGL, which is the browser's technology for 3D, showing 3D scenery and objects. You could yourselves make smaller or bigger canvases, but this is a good size for most people, and it should work on older or less powerful computers. Great. So let's create. Actually, it's worth just reminding ourselves. It's worth noting that we've previously looked at 3D before. We've done a series of tutorials, and I'm going to just load them again, some of them, just so you can see what they were like. So this was the one we did a long time ago, and it just showed, there you go, create canvas, WebGL, create a light with a direction, and a color, and we just create a sphere, and that creates a sphere there. You can see it, which is being lit. So it's got a light and a darker part depending on where that light was. So that's really simple. As I say, do go back to those earlier videos to be reminded of how we did simple 3D objects. Worth looking through the slightly more advanced, well, not more advanced, just a slightly more interesting example where we use the mouse pointer to rotate the 3D object, and this one's a cube, not a sphere, because rotating a sphere isn't that interesting. And again, you can see we create a canvas that's of type WebGL, and we use the mouse position XY, we create an ambient light, again a directional light, and then we create a box. Here we actually rotate the view rather than the box. So in this model under WebGL, you create objects, but you don't really specify where they are. You create their size. It was just like the sphere. You tell it, you specify its radius. Here we specify its width, height, and length. But we rotate the whole universe if we want to move it, or translate it if we want to move it somewhere else. Here's one that moves it according to time. Again, very simple to look at. To refresh ourselves, you can add textures if you wanted and create more interesting scenes. Again, these are things we've done before, so do go back and have a look. Right. So we will begin a shape. We want to create almost like a 3D version of a curve, which should be like a surface in some sense. Begin shape, end shape, and we call it close. Right, so let's start defining the points which our 3D curve will go through. So remember, this time it's got X, Y, Z. We'll just put some our own made up numbers just to make sure it works. It's always good practice to try something simple to make sure it works first before you get more complicated. So in this one, 0, 0 is in the middle of the canvas, or the 3D world that this 3D universe now that we've created with WebGL. So let's create one where it goes through 0, 0, 100. And I'm going to just copy that to make it easier. Goes through 50, 50, let's just see what that looks like. Not visible. Maybe I need to create more points. There you go, something's starting to appear. If I add more points to it, this one's a slightly further out point. There you go, you can see that there's a shape there that is created with XYZ points, and it's a curve, but it's a surface in that 3D space. Let's see if we can rotate it around. So what I'm going to do is, because draw is called repeatedly, I'm going to blank it. So this is a way of blanking it's like animation, creating a blank canvas first. Let's call it 0, 0, 0. That's a black. Reset the kind of canvas to black. And then I'm going to rotate around the Y axis, and I'm going to use a frame count. So frame count is the count for how many times this draw function is called. Remember, it's called many times. In fact, it is called many times by default, but simple turns it off. So we need to re-enable it with a loop. There you go. So loop means call draw repeatedly, and then every time it calls it, frame count is increased by 1. That's actually a very rough definition. I think the real specific definition is the frames that the browser has done, rather than how many times this has been called. In fact, let's look it up just out of interest. Frame count P5.js. Not that it matters too much. So it's the number of frames that have been displayed since the program started. Right. For our purposes, it's a number that kind of increases over time. So as this is increasing, it'll rotate an increasing amount. So let's look at that. So you can see this 3D shape is rotating around the y-axis. Now, you might think, hang on, with the picture that I drew over here, Z was upwards, and that was fine. What's actually happening in P5.js is that it's X, Y, and Z is, depth into the screen, but it's not a major, if we got those the wrong way around, it wouldn't spoil the effect. So you could always try to remember which way around it is, or just experiment, and it either creates a happy accident, or if you don't like the effect, you can always change X, Y, Z around. So there you go. That's quite nice, isn't it? Let's just for fun get it to rotate around the x-axis just to see what that looks like. So you can see that's going, like doing a loop over and over. And in fact, you can have both rotated. So in effect, the axis becomes a different one. So rotating around the X and Y will mean it rotates around an axis which is diagonal. Quite nice, eh? Very cool. Now imagine these, this surface that we're rotating, this surface is actually inside the marble. So what we want to do is move around that marble as we create. Do you remember moving around this marble and create some of these surfaces that are inside this sphere? And you can have a plan for doing that, or you can just experiment and see where it takes you. Let's start just by experimenting, starting with the basics first, which is just to move around that sphere in a systematic way, starting at the North Pole, moving to the south, and going around the planet, as it were, around the marble. So let's start with the idea of an angle. So for var, A for angle, that was our alpha here, which is the one that's going around like this. That's alpha or A. That's there. So that starts at 0. We'll go up to 180 degrees and we'll increase it by, let's say, 2. So we're going from the North Pole to the South Pole in angle increments of 2. Remember, 180 degrees is halfway around the circle, and 360 takes us back to where we were. And let's calculate from that our x, y, z coordinates. So var x equals, now remember it was the effective, let's type as we think, our effective radius times the sine of that angle. The effective radius, we've just put in brackets for now, times the sine of the alpha. And that makes sense, just as a check. When alpha is small, we're at the North Pole, sine of 0 is 0, so we're not moved away from in the x direction at all. And the same happens with y, the effective radius times sine alpha. So the effective radius of that sliced circle was r sine theta, and then x and y was the cos and sine of the other angle around, which we call theta, which described how we were moving around the Earth in this direction. So let's call that the real radius of the sphere times cos, and that angle is beta cos. We haven't defined these yet, and that's okay. We're going to do that. It's up to us how we define it. Let's make b depend on a. So let's call it a times 10, so that for every degree we move from the North Pole to the South Pole, we actually move around 10 times as fast, going horizontally around the Earth. Let's try that. And then var z, remember we don't have this component, that one, we don't have that, so it's just the effective radius, so r times sine alpha. And now we can draw something at that point. Curve, vertex, x, y, z. That becomes the point. Let's see what this ends up looking like. I'm not sure how this will turn out. This might be a little too dense in terms of points for a sphere. Let's just see what it looks like. Ooh. We haven't defined r. Let's say var r equals 200. Let's just say that. That's the radius of the sphere. So there's nothing visible there. Right, I've just spotted mistakes. That should have been sine. That should have been cos. So z is r cos alpha, and those two can't be the same, x and y. So x was the cos of b and the other one was sine. In this example, it doesn't matter if you get them the wrong way around, but if they're exactly the same, then they'll go wrong, because then x and y will always be the same, and that won't plot point around a sphere. So let's see what that looks like. Will this be a 3D curved surface that goes around, or is enclosed by, in some sense, a sphere? Let's see. Oh cool, that kind of worked. So you can see the edges of this curve are moving around a sphere. If we increase the resolution, in some sense, of that, let's see if that makes it. There you go, that's kind of easier to see there, isn't it? You can see we're working around that sphere. Let's draw another picture. So what we're doing is we're moving around A, or alpha, from the North Pole all the way down to the South Pole, that way, alpha. And as we do so, we're also, I'll change colour so you can see it, we're also moving around this slice. So if that's a slice, we're moving around that as well, so around this circle. So we've got two angles, we've got B and A, and we are putting points. Let's draw that again. So pick a different colour. So we might put a point there, and as we move, as alpha grows, or A grows, we're also moving around that slice 10 times faster actually. So we are kind of doing that with our points, marking those points, the curved vertex points, through which this kind of 3D surface is going to touch and go through. So that's quite cool. It's simple, really. It's much easier to. I really encourage you to draw pictures like this, sketches, to see how it all kind of fits together and how it might work. If I just said, if I just write those mathematical expressions, they're harder to work out. Whereas if we draw narrative pictures and say, look, A is going round like that, and then B is going round like that, and B is 10 times A, means it's going round faster. It kind of starts, it's easier to visualize what's going on. So that's nice. But in a marble, these things are sort of translucent a little bit, and they're also, we might even have more than one. If they're translucent, it might make a nice effect to have several of these kind of squeezed into the sphere. So let's do the translucency thing first. In fact, I'm going to switch over to the HSB color scheme, color mode, and again go back to that previous few videos where we introduced different color modes. RGB is the normal one, red, green, blue, but HSB, hue, saturation, brightness, is much easier to think about in color now. You might say that sounds crazy. Of course RGB is the one that we're all used to, but as soon as you start getting used to HSB, it suddenly makes a lot more sense. So I do encourage you to go back and have a look at those. So I'm going to switch to HSB. I'm going to make those strokes, the edge, the drawing, the edge of that kind of surface. I could turn it off, but I'm going to turn it to half, which means it'll be a thinner edge, just because we want to still see it. The background now has to be in HSB, not red, green, blue. So 0, 0, brightness. Let's make it 100. And let's say the fill is say, so remember hue goes from 0 to 360. Let's say 360. Let's pick a color first. Let's call it 0, which will be red. I think yellow is the one we've been working with, which might be 30 degrees. And then saturation 80, brightness 80, and then alpha 0.4 out of 1. And then let's also do the stroke as well to have that. Let's call it 30 for yellow. Actually make that red. 80, 80. I seem to use 80 and 80 a lot for saturation brightness. And then 0.8, so it's a little less translucent, so it's easier to see. Let's see what that looks like now. Cool. Now the translucency has really started to work there, hasn't it? Really nice. That's quite nice as it is. You could almost just stop there. But again, this looks moderately sophisticated, but it came from simple ideas sketched out with a pen and paper without too much regard for neatness and tidiness. But that's the important bit in creative coding. It's the idea. The coding bit is a formality in some sense. It's the ideas that are important. It's these sketches that are more important than the code itself, in my opinion. So let's try and have several of those foils, as it were, and we'll have them at different effective radiuses. So what I mean by that is we'll do it once with a radius of, say, 200 of that marble. Then we'll do it again, and we'll reduce the radius, and we'll kind of, so this is the first one, and then we'll do another one inside at a different color. Then we'll do another one inside that at a different color, like that, maybe like that. So all the time we're effectively reducing the radius of the marble, and we can do it from outside in or inside out. Let's do it inside out. So to do that, instead of having constant r, we're saying for, I'll be creating a loop, for var radius is, let's start at size 40, go up to 200, up to and including 200, and we'll increase it by 40 each time. and that will be bounded around the shape. So all of that happens inside. Now we can make the colour depend on R. So let's say R times 2. Why have I said R times 2? Well, in HSB, the hue, the colour, goes from 0 to 360. So if I say 0 to 200 is the maximum, 0 to 400, that's okay, it just wraps around. So let's try that and see what happens. Cool. That's quite nice, isn't it? So you can almost, it's not quite a marble, it didn't quite achieve that effect, but there are some interesting colours going on here, which is nice. Let's just adjust how fast we go around. So 20 times, let's go 10 times. Okay, let's see what happens if we go around at the same rate. Yeah, not as interesting. A nice design, but not quite as interesting. Let's see if it go around twice as fast. That's interesting. Let's say 40. Wow. So I think that first value, maybe 20 or 10, is probably around right. What I'm going to do now is just perturb these so they're less perfect. I'm going to add some noise. So what I mean by that is, let's draw a picture. So what I'm going to do is, if you remember noise, it's like randomness, but it's smoothed. So randomness would be any kind of value between an upper and lower range, but smoothness depends on a parameter, let's say parameter p, and it means that when noise is picked and the p-values are close to each other, the random noise is similar as well. So you have smooth changes, random but smooth. Again, there's a video earlier on that talks about noise. It's really powerful idea, really important, I think, to know about it. So we're going to use noise to perturb this the position that the surface goes through. Now I'm just going to think, where do I want it? Do I want to perturb alpha a little bit, or do I want to perturb beta a little bit, or do I want to perturb the radius? Well, you could try all three actually. It's up to you. I mean, it's part of the fun, isn't it? What I might do is I might just perturb x and y just to keep it simple. That's probably the simplest thing to do, so I'll invent a noise variable. Let's call it var n equals, and it depends on noise, when noise is built in. Let's make it depend on, what's the parameter? You could play with different ones. The idea really is that noise varies with this parameter in a smooth way. So we could say noise depends on the radius plus a angle, how far down we've gone. And then, because noise is from 0 to 1, I'm going to scale it up. I could, and I want it to be from, say, -1 to +1. So what you could do is say 0 to 1, so -0.5, -0.5. That goes from -0.5 to +0.5, and or I could actually just have it all additive, so not negative. So I could say, let's scale it. So instead of 0 to 1, it's, let's think of a number, 0.4. So it goes from 0 to 0.4, and then I'm going to uplift it by a constant amount, let's say 0.8. That means it's going to go from 0.8 up to 1.2. So I'm having my noise vary between 0.8 and 1.2, so varying about 1. So my noise is around 1. We got there in the end. It'd be nice if noise had parameters that said between these values in terms of its output, so input and also output. Maybe that's something for the future. Great, so that's a noisy variable that we've created, and we could say just perturb x and y so that its average will be 1, but it could be 0.8 times or 1.2 times, but mostly be around 1 time. So it's not going to stretch it too much. Let's see what effect that has. Cool, nice. You can see it's it perturbed it a bit, it distorted it a little bit. It's quite nice. Let's see what happens if we change the background to black. Does that improve the look? It's a different look. I think I prefer it white. You can have a play yourselves with maybe perturbing the angle or perturbing how far around we've gone. I've just kept it simple by just knocking x and y a little bit. Cool, so although we didn't quite recreate a glass marble, we have created an interesting effect, and it's based on those ideas of trigonometry, moving around a circle, taking that into the 3D world, playing with some sketches to understand how we move around that sphere, and seeing what effect comes out, and just trying to kind of stretch this idea of a curve into a 3D kind of surface. Nice. I'll stop there. We could carry on experimenting and refining and playing with it, but you should do that. It's really important to experiment and break things and try things, because in the end nothing really breaks, it's just code in a browser, but you learn a lot by doing it. You find things that you like, patterns that you like experimenting with. So yeah, have a go. I'll create a link for this code so you can take it if you don't want to kind of type it all in yourselves, and have fun with that. Fantastic. I hope you enjoyed that, and we'll see you again soon. Bye.